So this video is for our asynchronous day, which is Friday, March 5th. This is on assignment classwork 10-61 to 64, which is what you guys are going to be doing in class. And I'm making a video on it. I would like for you guys to try it first and then come to the video for help. The first thing I do want to talk about real quick is a couple of ideas we should have understood from yesterday. So let me just discuss that. So first I wanted to remind us of what we learned the other day. We had the arc, we were folding it to trying to find a center. When I folded it, I folded A onto B, which made this bisect this line segment. And we also saw, and it went through the center of my circle, okay? And we saw that that not only bisected it, but it bisected it in a perpendicular manner, okay? So when you have a chord cut by a perpendicular bisector, it will go through the center of your circle. Okay, that's what we wanted to see from yesterday. And one problem I want to share with you real quick is the following. So this is going to use that idea that I was just talking about in a problem like this. So we have a circle with a chord WX and Z is the center of our circle. We know that WX is 8, so this to here is 8. We also know that the radius of the circle is 5, and we want to figure out how far is this chord from the center Z, okay? So some of the information I'm going to put in here, let me just get this a little zoomed in more. I know that drawing from Z to this point, this would be a radius, and that radius is 5. They told us that, okay? I also know that if I draw a perpendicular bisector, it has, of this chord, it has to go through the center. So I'm going to draw this in red, okay? So if I was drawing a perpendicular bisector, okay, so I'm saying that this is perpendicular and it is bisecting it. It has to go through the center. That's what we just saw. So if it's bisecting this, which was 8, now this is going to be 4 and this is going to be 4. So I have a triangle here. Now this triangle is a right triangle, again, because this is a perpendicular bisector. So I can use Pythagorean, and if this is 4 and my hypotenuse is 5, then I know that this length right here is going to be 3, because that's a 3, 4, 5 right triangle. So that's something that they want us to see, okay? So now I'm going to be going to the worksheet for today. I'm going to show a little video first, just kind of giving you a little bit of history about the problem, and then we're going to get going.
How would you set about to measure the Earth with the mathematical knowledge and tools you already possess? A Greek named Eratosthenes did it 240 years before Christ. He was head of the great library of Alexandria in Egypt, a city built by the Greeks. He, like others, suspected that the world was round. After all, the sun and the moon were round. He had also noticed that the sun's rays fell in parallel lines. Greeks before him had divided the circle into degrees and had measured angles. With this information and a logical mind, he measured the Earth. Here is how. While visiting the city of Syene one midsummer's day, Eratosthenes noticed that the reflection of the sun could be seen in the bottom of a deep well. The sun was overhead, and the rays pointed to the center of the Earth. He remembered this, and on the next midsummer's day in Alexandria, he measured the shadow cast by an obelisk. Sunbeams travel in parallel lines. So the difference in angle had to result from the curvature of the Earth. If the angle was 1/50th of a circle, then the distance around the world must be 50 times the distance from Alexandria to Syene. With these simple tools, Eratosthenes made this almost exact measurement of the world more than 1,700 years before Magellan sailed around it. He was a friend of Archimedes. He was a mathematician and a poet, invented the sieve for finding prime numbers, was the first geographer, and corrected the calendar to the one we use today.
So that little video was dealing with this first problem that we are going to be working on. Okay, we're going to be doing the math that he was doing. So we know that the distance between the two towns was 500 miles. Okay. We also, in the picture, see the sun rays coming. Okay. And we are going to try to figure out a couple of different things. We need to figure out we know that that the meter stick from his experiment today, then the stick shadow in Alexandria would be 127 millimeters long. Determine the angle of theta that the sun's rays make with the meter stick. Remember that a meter stick is 1,000 meters long. Assuming that the sun's rays are essentially parallel, determine the central angle of the circle if the angle passes through Alexandria and Syene. How did you calculate your answer? Also here, we see that this is 500 miles, okay? Since the distance along the Earth's surface from Alexandria to Syene is about 500 miles, this is the same as the length of the arc between Alexandria and Syene. Use this information to approximate the circumference of the Earth, and then we're going to try to figure out the radius of the Earth. Now, I have a worksheet here that you guys can use to do all that math. Okay, so we're going to fill in some information that we know here. So I drew in, we have parallel lines. Okay, the sun rays are parallel. That's what we saw in the video, and that's what they said in this problem. Okay, so I'm drawing in parallel lines. That's going to be important to us. Some of the important information that we need here. In part A here, it says that the stick shadow was 127 millimeters long, and that a meter stick is 1,000 millimeters. Okay, so I'm going to come back here and put those numbers in. So I know that the shadow here, this one right here, is 127 millimeters. Okay. I know that this right here, the stick, is 1,000 millimeters. Now, what they want us to find is this angle here. That's what they want us to find. Now, we know that this is a right triangle. We know that this is opposite. We know that this side here is our adjacent. And we know that this one here where the sun's rays are, this would be our hypotenuse. So I need to find that angle theta. So I'm going to think of TOA. And so I have opposite and adjacent, so I'm going to be using tangent. Okay, so I am going to do tangent of theta is equal to opposite over adjacent. Now I need to find theta. So to find theta, I have to do the inverse. So I know theta is going to equal tan inverse of 127 over 1,000. So I'm going to put that into my calculator, making sure that my calculator is in degrees. So I'm going to do tan inverse of 127 divided by 1,000. And I end up with 7.24, or well, let's be a little more accurate, 7.238 degrees, 7.238 degrees. Okay, so 7.238 degrees. That is what theta is equal to. Okay. So I'm going to go back to this worksheet here. Okay, and it says determine the angle the sun rays make with the meter stick. So theta is equal to 7.238 degrees. Now, assuming that the sun's rays are essentially parallel, determine the central angle of the circle if the angle passes through Alexandria and Syene. How did you calculate your answer? Okay, so now what they want is this angle, okay? They want this angle right here. That's the central angle that they're looking for, okay? So what I'm going to do is I know that we have parallel lines, okay? We have parallel lines right here, parallel lines, and I have a transversal here, okay? So I have parallel lines cut by a transversal. Okay, so this transversal, so that means this angle here and this angle here, because our alternate interior angles are going to be the same. Okay, alternate interior angles. So when I come back here and they ask what that angle is, it is going to be the same as this. Okay. And when they ask how did we calculate that, okay, we calculated it because parallel lines cut by a transversal, we had alternate interior angles. So this was from alternate interior angles. Now, the next part is saying that we know that this right here is 500 miles, okay? Since the distance along the Earth's surface from Alexandria to Syene is about 500 miles, this is the same as the length of the arc between Alexandria and Syene. Use this information to approximate the circumference of the Earth, okay? The circumference of the Earth. So what we want to figure out is we have 500. So we know that circumference is equal to 2 pi r, right? And we know that we have, so I know that, again, circumference is equal to 2 pi r. And that 500 is not the whole entire circumference, okay? I know it's part of it. I know that that 500, let me grab something to write with here. I know that that 500 is equal to part of my circumference, 7.238 out of 360. That's what part I have of the circle. And that's what part of the circumference the 500 is. And circumference is 2 pi r. So I am going to just do the math. I am going to take 500 times, so let me just get my calculator up. So I am going to take 500 times 360, which is 1,000, sorry, 180,000. Okay. So I have 180,000 is equal to 7.238 times 2 pi r. Okay, and 2 pi r is my circumference. So then I want to divide both sides by that 7.238. And so when I do that, I divide it by 7.238, I get that my circumference is about 24,800 and about 69. Okay, about. That's my 2 pi r, which is my circumference. Okay. So now use your result from part C to approximate the radius. Okay. So if I continue with my equation, and I know that 24,869 is equal to circumference, and circumference is 2 pi r, I can figure out my r by dividing by 2 pi. Okay, so I'm going to divide by 2 pi. Now, when you're doing this on the calculator, you need to be careful. Okay, so if I am taking this answer and I'm dividing it by 2 pi, don't go to pi like that, because it's going to divide by 2 and then times by pi. So I'm going to go parenthesis 2 pi. And I ended up getting 3,900 and about 58 miles. So 3,900 and about 58 miles. Okay. Okay. Now on this part, what we're going to be doing is we're going to be kind of seeing relationships between the central angle and the arc. So it says to determine the circumference of the Earth, we used an angle that its vertex is at the center of the circle. Like the angles and polygons that you studied in chapter 8, this is called the central angle. So this angle right here that comes from the center out, this 40 degrees is a central angle. An arc is a connected part of a circle. Every central angle has a corresponding arc. So the corresponding arc to this angle, STU, is this arc SU. Okay. Since the measure of the central angle helps us know it's part of the whole 360 degrees of a circle, its arc can also be measured in degrees. Thus, the measure of an arc is defined to be equal to the measure of its corresponding central angle. So you have to be careful with what we were calling an arc length. And an arc length would be like this 500 that was here. That's part of our circumference. That's an arc length. That is not an angle measure. This right now, this 40 degrees right here, that's the angle of this. That's called an arc measure. So we have to be careful with those terms, okay? So if I'm just looking at the distance here, that is arc length. But when I am looking at it in terms of this angle, okay, this 40 degrees, that's called an arc measure, okay? So arc length is the circumference, the part of the circumference, and arc measure is the angle. Okay, so examine the central angle, the circle above. What is the measure of SU? Written measure SU. And this should have had an arc on it. Sorry, I don't know why that arc did not come in. Okay, should have had arcs on those. Okay, show how you got your answer. So what is the measure of SU? okay? And what is the measure of SZU? So SU is 40, okay, because the central angle is 40. So again, the measure of arc SU was 40 degrees. And they want us to find this other arc. And this arc right here is the major arc. Now, if SU is 40 degrees, that means that the rest of it, okay, the rest of it has to be 320 degrees. So when we are doing this and we are trying to figure out the major arc, I'm going to take 360 minus the minor, and what's left is 320 degrees. And so that's what it is. Together, that minor and major have to add up to that 360 degrees. Okay, now here they're talking about that arc length. So when he was saying that he was 500 miles away from Syene to Alexandria, that is an arc length. Okay, that 500 was the arc length. The central angle in the picture, let me just go back to it. Okay, so the arc length, this was the arc length. This central angle was the 7.238. That was the central angle. That is an arc measure. The 500, which is part of the circumference, is an arc length. So here it says, one way to determine an arc length is to wrap a string about a part of a circle and then straighten it out and measure its length. However, if a figure is not drawn to scale or it's too large to measure directly, or you don't have any yarn on you, then you must calculate the arc length using other information. Calculate the arc length of SU above. If the radius of the circle T is 12 inches. Okay, so we know that the radius of circle T is 12 inches. And they want us to find the arc length of SU. So they want us to find this that I'm kind of coloring it in black. So that is circumference, part of a circumference. So we are going to take our circumference, which is 2 pi r. So we're going to end up having 2 pi times our 12. Now we don't have the whole entire circumference. We had part. We had 40 out of 360 degrees. And then we're going to work that out. And so if I put that into my calculator, okay, so I am going to, here, I'm going to start with my 40 over 360 times 2 pi times 12. And we end up with 8.38 about. So 8.38. And if we want to do it as a, leave it in pi form, and I didn't put the pi in my calculator, we would have ended up with 8 pi thirds when we work that out. So 10-63, inscribed angles. In the diagram at the right, angle BDC is called an inscribed angle. This is an angle where it touches one side of the circle, okay? So the vertex lies on the circle. This one here, the vertex does not lie on the circle. This one actually is at the center of our circle. So this one is a central angle. This is an inscribed angle, okay? So angle BDC is an example of an inscribed angle because it lies within circle A and its vertex lies on the circle. It corresponds to central angle BAC because they both intercept the same arc BC. So here, oops, doesn't help doing it in black. Let me get a different color. Okay, so you'll see this BDCD, that angle there, BDC, forms this arc BC. We say it intercepts it. It's the intercepted arc. Okay. And this BAC, which is our central angle, also is the same intercepted arc. And we want to find the relationship between these. So what you might want to do is use either, if you have like some paper that's see-through, if you have maybe a page protector you can use with a marker, an expo marker, or maybe a permanent marker if you don't care about the page protector. Again, I am going to use, I found some wrapping tissue paper that I'm going to use kind of as my tracing paper, okay, for this. So what we're going to do is we are going to try to figure out a relationship here. We have an angle F, angle G, and angle H, and all of these are inscribed. So I'm going to draw these. This is angle F, okay. This one is angle G, and this one is angle H. Okay, those are all inscribed angles because they all have a vertex touching the circle. Use tracing paper, or even you can use like a Ziploc bag maybe, if you don't have any page protector, and use like a marker. Okay, and what they want you to do is to trace them and compare them. So I'm going to get that situated. I'm going to trace them and then I'm going to compare them. So I am going to trace these. Let's see if I can do this pen here. Okay. Got that one. Okay. And now what I'm going to do, now that I've traced them, I'm going to try to compare them. So right now, if I'm looking at this, I'm taking angle F, and angle F actually fits on angle G here. Let's see, maybe I need to shine some light on it so you guys can see better. And angle F actually also fit on angle H when I'm doing this, okay? So now I'm using H, and H fit on top of G, and it fit on top of F. So these angles here are all the same. And what they want you to pay attention to is that these angles, let me just grab my thing here. These angles all are so these angles all form this arc JK. All of them form this arc JK. So you'll notice that F, it's JFK, it's JGK, it's JHK. So when you have an inscribed angle that intercepts an arc, and you have another inscribed angle that also intercepts that same arc, they are going to be the same measure. Okay, so angle F, angle G, and angle H all are going to be the same measure. Okay, so all are same measure. Okay, and that's every single time you have inscribed angles making the same intercepted arc. Now, there's another situation here. We have an an inscribed angle X, and we have a central angle Z. Now notice both of them are forming WY, arc WY. So let's see, is X and Y the same? So here, remember, each of these were forming the same arc and they were all equal. So I'm going to trace these and let's see what happens. So I'm going to trace right now angle X. Okay. And I am going to see if it is the same as the angle Z. And I see it is not the same. Okay. Angle Z is bigger. So what I'm going to do is I'm going to take this and I'm going to get another one of these. Okay, so I'm going to get, so I'm lining it up so I can basically make two of these angle X's. Okay. And so now I'm going to take these two angle X's and I'm going to compare it to this angle Z. And so when I do that, I know it's kind of hard for you guys to see it, but what happens is it ends up being on top of that angle. So two of my X's, okay, that's what I put here. Two of my X's make up one of my Z's, okay? Two of my X's make up one of my Z. So this angle X here, if I double this angle, I get angle Z. If I take half of angle Z, I get angle X. That is their relationship. So again, if I was to take two of these angles, it actually made up this angle C. So two of my green ones made up my purple one. And again, you want to notice that both of them have the same intercepted arc. So when I have an inscribed angle, okay, let's say I call this X. My central angle that also forms the same intercepted angle, arc is going to be twice that every single time. And whatever my central angle is, my arc measure is going to be. Okay, that's what's going on with these. So we're going to use that idea when we're dealing with these problems down here. Okay, so this 118 is the arc measure for this. Okay, it's the arc measure. We have 118 out of 360. And we want to know what this angle X is. And this angle X is going to be half of that. Okay, it's going to end up being half of that. So we're going to end up getting, again, let me just make sure we understand, 118 divided by 2, and that is 59. and that's what angle X is. Now on letter B, I have this inscribed angle. Okay, this angle is 41. So I'm going to take that 41. I am going to double it, which is 82. And that's what my arc measure is going to be. On C, I know that this is 78. I have a right angle. Now, if that is 78, and let me kind of color code it, it is forming this arc. So this angle, inscribed angle, is forming that arc. So that is going to be 78 times 2, and 78 times 2 is 156. So my Y is 156. That's what my Y is. Okay. Now let me kind of clean this up here. So let's see the rest of the problem. I need to figure out Z. Well, if I know that this right here is 78, this is half of a circle. So this is going to be 180. There's a couple ways to think about this, okay, for the 180. One way to think about it is this is a 90 degrees and it is its inscribed angle. Okay, hold on, let me get rid of that. So one way to think about it is this inscribed angle is 90. So this intercepted arc has to be twice that, which is 180. That's one way to think about it. Another way to think about it is you see that this is a diameter. So that's cutting my circle in half. So this has to be 180. So I know that that's 180 degrees. I know that this one is 156 degrees. Okay, so let me just do this. I know that this is 156 degrees. I know that this is, let me just get rid of this line here. I know that this is 180 degrees. So I can figure out the rest by taking 360 minus those. So I'm going to go 360 minus 180, which is 180, minus 156. And so when I take 360 minus 180 minus 156, I end up with 24. So this is 24 degrees. Okay. On letter D. Okay, I know that my central angle is 56. Whatever my central angle is, so is my arc measure. And then since these both have the same arc that they form, this inscribed angle is going to be half of 56. Okay, it's going to be half of 56, and that is going to be 28 degrees. So my Y is 28 degrees. On E, I know that this is 114, which means my X is also 114 because that's a central angle. So it's going to be same as its intercepted arc. Now, you also have this angle here, Y, and notice Y also forms that same intercepted arc, but it's an inscribed angle. So it's not going to be 114. it's going to be 114 divided by 2, and 114 divided by 2 is 57. So that's what my y is. My y is 57. On this one, I have this angle here, which is inscribed as 28, which means that this is going to be 28 times 2, or 56. Now, this angle here also forms that same arc, so it has to be the same as my other inscribed angle. It is 28. So you're going to be seeing a little bit of this on your homework along with review.